Have you ever stopped to appreciate a computer crash? I know, let's be real for a second. Usually when your screen randomly buffers, an image totally distorts, or a file corrupts, your first reaction is just pure frustration, right? But what if I told you that those everyday moments of digital failure actually reveal a hidden, incredibly fascinating world? Welcome to The Explainer. Today, we're taking a deep dive into the hidden mechanics of digital media. We're going to be drawing heavily on Rosa Menkman's absolutely brilliant theoretical work, The Glitch Momentum. It's going to help us unpack what really happens when our technology breaks down, and honestly, why those breaks are so crucial for us to understand. Okay, so here's our roadmap for today. First up, the perfect transmission myth. Then we'll hit the Glitch Studies Manifesto, dive into the anatomy of noise artifacts, break down some file formats, and finally, look at the shift from artifact to commodity. Let's get into it. Section 1, the perfect transmission myth. For decades, the tech industry's ultimate dream has been this idea of the optimally transparent channel, basically making the medium completely disappear to give you an illusion of a pure, uninterrupted experience. But to get why that transparency is totally a myth, we have to rewind to Claude Shannon's 1948 mathematical model of communication. While working at Bell Labs, Shannon designed this linear progression to optimize the signal-to-noise ratio. And it seems super simple, right? Information just goes from a source to a transmitter, over to a receiver, and bam, finally hits its destination. Well, here is the complication. Shannon and Weaver eventually had to add a highly disruptive sixth factor to this neat little model, a noise source. You see, external noise inevitably gets introduced right before the received signal while the data's in transit. It completely obscures the purity of the signal. So, reality check, the communication channel is never truly empty, and it's certainly never perfectly transparent. So, the absolutely crucial takeaway here is that exact perfect transmission, it's literally impossible. It all comes down to a fundamental concept called entropy, which dictates that any system naturally tends toward disorder. But here is the truly wild part. Information actually requires this encoded entropic noise to be contextualized and transmitted successfully. Without noise, there is no information. It's an unavoidable trait built right into the message itself. Crazy, right? Moving on to Section 2, the Glitch Studies Manifesto. This brings us to a massive pivot. We're moving from engineering mathematics straight into digital visual art. We can directly contrast the strict engineering search for transparency with the philosophy of digital artists like Namjoon Paik and Rosa Menkman. See, while engineers are desperately trying to build this impossible noiseless channel, these artists treat the digital signal as a physical material and process. To them, the medium isn't supposed to be invisible. No, it is meant to be bent, broken, and interrogated. Menkman actually lays this out beautifully in her manifesto, urging creators to use the glitch as an exoskeleton for progress. Just think about that for a second. Instead of hiding the noise, glitch artists use it as a rebel solution. They are actively fighting against the homogenization of everyday media by purposely interrupting the predictable, linear flow of information. They are forcing us to actually see the technology that we take for granted every single day. Section 3, Anatomy of Noise Artifacts. So, how exactly do our modern technologies try to compress and hide all this noise? And what does it actually look like when those systems fail? Well, there are three primary categories of technological interruption. We've got encoding and decoding, which is compression, signal corruption, which happens during transmission, and feedback. By far, compression is the most common way our tech is constantly reorganizing time, space, and data to make your files travel faster across the internet. But, not all compressions are created equal. We have lossless compression, which faithfully retains all of the original information. And then we have lossy compression, which takes a much more pragmatic, sometimes ruthless approach. Actually, I want to remind you of something right now. The very phone or computer you are watching this explainer on is constantly performing lossy compressions. Behind your back, it is permanently throwing away data that the software algorithms assume your eyes or ears just won't notice, all in the ruthless pursuit of speed. Section 4, Breaking Down File Formats. Okay, we are going to visually explode some of the familiar file formats you use every single day. We want to see exactly why they break the way they do when we introduce glitches. First, here is our baseline. This is an uncompressed original raw video still image. This file format contains minimally processed data directly from a camera sensor. Because it is totally uncompressed, it holds a massive amount of pure data just waiting to be manipulated. Now look at what happens when we mess with the code. By simply copying and pasting random data into a BMP file, a process known as data bending, we get this incredible visual break. You can literally see how the upper half of the image data shifts horizontally, but the bottom half remains completely intact. That is not random. It happens because BMP files process pixels in a reverse bottom-up raster scan. The top broke because we altered the data flow, but the bottom hadn't even been rendered yet. How cool is that? Now let's talk about GIFs, which are notorious because they only support a maximum of 256 colors. When a GIF tries to render a super complex image, it just has to discard unavailable colors. If it does this poorly, you get harsh truncation, causing what's called a quantization error, those blocky, flat, ugly patches of gray. But if the algorithm intentionally adds noise, a brilliant process called dithering, it strategically scrambles the pixels. This actually tricks your eye into seeing a smoother approximation of color depth. So in this case, noise is literally fixing the image. Let's look at one more GIF variation. When a random error is introduced to an interlaced GIF, it generates these really jagged, horizontal, combing artifacts. Why does it look like that? Well, because the interlaced format weaves different rows of pixels together at different times. When the timing or the data gets corrupted, the weaving just fails, literally pulling the image apart at the seams. Section 5. From artifact to commodity. Okay, so we've seen how beautiful and revealing these digital errors can be. But what happens when raw, chaotic destruction becomes, fashionable? Rosa Menkman calls this the ossification of glitch, when the avant-garde becomes a commodity. As these radical digital mishaps get popularized, they shift away from being true, unpredictable accidents. They become predestined. They transition from being this punk rock break in the system into a totally standardized, expected design choice. I mean, you see this everywhere now, right? What begins as an unpredictable, genuine glitch in a system's logic eventually gentrifies. It turns into an easily reproducible glitch effect, fully automated by software and plugins. The radical, disruptive artifact is basically tamed into a simulated filtered effect that anyone can apply to a photo on social media with just the tap of a button. Which leaves us with a really fascinating paradox to consider. When every single digital glitch becomes an automated, fashionable filter, carefully engineered to look broken while actually functioning perfectly, where will we find the next true break in the system? Thanks so much for joining me for this explainer. I really hope it completely changes the way you look at your next digital error.